Can we try the volume?
Absolutely.
Brandon, the last thing
Absolutely.
we need to do is you need his voice to present.
Yeah, you can actually just use the microphone.
Absolutely. Yeah.
So can I just
Could you speak again for us? We can test it out.
can you hear me? At the back?
Would you want to bring the microphone to your lapel on your shirt? There you go.
Yeah, okay. Can you hear me now? So volume and can you turn on your Zoom to make sure?
Yes, you're right. Sorry. Should I post it?
Okay. That's it.
Can you speak one more time for us, sir?
Is it audible? Must be better. Yes, sir.
Yes.
Yeah, sure. How much? How long do you want me to speak?
We're just trying to fix it so the lecture works.
It was looking well, I thought.
Yesterday it worked well, but yes, it's going to work well for the people in the room. Yeah, very well.
Okay, so we've got one link bridge. Sounds good.
Yeah, sure. I think the politics are crazy. Okay. Are you students here? Are you students here?
Yes, I'm an undergraduate.
Okay.
Are you going now? No. How about after the lunch? Because I'm a little
Morning, Grisha.
So you really go from micro to ultra.
No, I don't know about ultra far. Yeah, that's right, exactly. Yes. That's where the real substance is. Whenever you approve, whenever you say we can start, we'll start.
We all know, second lecture.
Thank you. Thank you, Peter. Thank you. I hurried Peter up because I need no introduction. Since yesterday, there was a really elaborate introduction, and thank you for that. Yesterday, I spoke about turbulence at very small scales. And today, I would like to say a little bit about large scales, very large scales. Not necessarily the largest that we can think of, but this be large enough for many purposes. And that's the fluid dynamics of the sun. And the sun is so-called a main sequence star. It just means the sun is middle-aged and doesn't do any crazy stuff. And we know a lot about the sun. Its mass, we know its age, we know nuclear reactions, surface temperature, such things very well. And quite rightly, astrophysicists take great pride in all that. But when I say less certainty exists about sun as a dynamical object, I have to explain this a little bit, just so I don't tread on anybody's toes. Once in a while, the sun sends out such huge excursions. They are called prominences and solar flares and all kinds of things. And they stretch out sometimes to 2 million kilometers or a few million kilometers away from the surface. And this particular one was taken from the NASA website for August 31st, 2012. And they sends out billions of tons of particles and also a lot of high energy radiation. And if one of them reaches the Earth, for instance, it has been estimated, this is a lot of work for a lot of people. They'll tell you how much it will cost because it'll fry all the satellites, so you won't have any internet, and it might even reach the surface of the Earth and fry all the electrical networks and things like that. But I just put in here how much it might cost if one of them hits the Earth. The damage is 20 Katrinas. $2 trillion or something doesn't make any sense to you because it is $2008. And so it's changed clearly. And this is what we would like to be able to say something about, this kind of thing, and not this particular thing. As a dynamic object, sun is responsible for many such things, and we should like to understand how they happen, how to predict them if possible, all of the usual stuff. Now, luckily for us, our knowledge of the sun is being accumulated at a very rapid rate because of all these heliophysics flight programs. So here is a function of time, 1994 down to here. These are names of all the various satellites that are flown for certain specific purposes. And the line here is simply the number of solar sunspots, but I will talk about it later. So it just shows there are a large number of them, and some of them are operational. And there's a whole lot of data that is indeed available. And NASA, for instance, spends a lot of money putting these satellites into orbit, but not enough money to understand what the data mean. So we, others who don't have any money from NASA tend to look at that. Now, so that's the point of my talk. And I want to point out that when I began working on this seriously, Boulder, in part, was a great inspiration for me. By Boulder, I mean not only the astrophysics group at the university, but also NCAR and UCAR and all the other things. They're all the same people somehow together. And they, I learned a lot from reading them. Since I'm giving the talk in Boulder, I should definitely acknowledge my indebtedness to Boulder as an institution. So if you want to understand phenomena like the one I am talking about, the reigning paradigm is that all the surface phenomena of the sun are driven by internal dynamics alone. You might ask, well, what else? Certainly there is no obvious external forcing, but there are, in fact, views that tell you at least certain phenomena on the surface of the sun are a result of external forcing. That's not a reigning paradigm, as I say. It's a paradigm that is somewhere in the nooks and corners of the field, and it arrives from the fact that while the sun's mass is about 99.9 or some percent of the mass in the solar system, the angular momentum is only 0.3%. It's really very small. If you take Jupiter, Jupiter has 62% of the total angular momentum in the solar system. And in fact, a lot of work on this statement here has appeared. As I say, it's not the reigning paradigm, but you should know there are other views, whether you actually work on them or not. And that is the period of Jupiter going around the sun, for instance, as exactly the periodicity in the sunspots, and 11.0 some years. And if you look at the spectral decomposition of the signals, they're so close to each other that, well, it could be a coincidence, but very interesting observations on which science thrives come from coincidences initially, you know, and you just look at it and then people start wondering why this is so, and it may lead to something. So this is something you should keep at the back of your mind, but not worry too much for now. So now if we accept the reigning paradigm, what is the internal dynamics? This is a picture I took also from the NASA website somewhere. And there is this central region, about 25% or so of the sun's radius, where it's very hot because of gravity of the sun and you know, the usual things why the central cores of these stars are very hot. And you have nuclear reaction fusion taking place, hydrogen to helium, and you have neutrinos that come out and they sort of wander away without any resistance. And there are these photons which eventually have to make their way out. And the nuclear reaction, let's say, stops at this boundary, hot. And thereafter, energy transport takes place by radiation. And the density of mass here is so immense that the photons take a very, very long time to escape this region. Usual Brownian motion type calculations say it takes, well, 100,000 years, for instance, for a photon to escape from here to there. Now, as we move outwards, the temperature drops, and at some point, for example, this radius, let's say, around here, the radiation itself is not competent to move the energy, and you need something else, and that is convection. The convection is what happens in this part of the sun, from the surface down to about 200 megameters, which is about a third or so of the sun's radius. And that's the one which is thought to really drive all the surface phenomena, including the magnetic activity and things like that. And our purpose is to understand this a little bit, as I said, assuming that it is not driven by something else. And in any case, most of the activity does come from convection. And this picture is very deceptive. It sort of suggests that the fluid goes from the bottom to the top and recycles itself because it's hotter here than it is there. The surface temperature we know is about 6,600 or some Kelvin. And this is the kind of very simple-minded cartoon of how convection is supposed to take place. In fact, if you look in astrophysics, it seems to me that when you say you understand something, it means you have a model and the model is understood. It's not like it's not like the fluid flow past the cylinder that Grisha was talking about. It's a little different in some sense. I don't really know how else one can do it. So in fact, what we need to do is to construct a model for convection. And okay, that's our goal. And of course, we will fall way short of it. And in fact, if you look at the reviews, like Basus, for instance, says, this sentence is repeated many places. The most important source of uncertainty in stellar models is our inability to model convection properly. That actually has a huge consequence for the stellar model, solar model itself. So, yeah.
I wanted to ask, what's the estimate for the temperature?
Yeah, I will tell you in a minute. But I could answer directly. So on the surface, you know what it is, 6,600, whatever. At the bottom of the convection region, it's about 1.5 million Kelvin. So it's a big difference in temperature between the. I will show you graphs and all that later on. So if you have a strong temperature difference, like the one I just mentioned, you would expect the convection to be vigorous. And I make some naive estimates for the convection in the sun. In convection in the sun, if it is a convection as a flow, if it is driven on a flat surface like this, so you take a container, you heat the bottom, and then you cool the top, and then the fluid rises and falls and rises and falls. And there are a few parameters that are of interest, which you all know about, but I will mention them anyway. One of them is the so-called Rayleigh number. Rayleigh number simply tells you what this temperature difference is between the top and the bottom, normalized by some other ways. Temperature difference is a driver, and the normalization is the result of viscous action that will slow it down and things like that. And if you set up an experiment in a lab, which without really going very gung-ho on it, you might get 10 to the power 10, something like that. The record today is 10 to the power 17. It's an experiment in which I was involved, so I might as well tell you about it. So if you calculate the Rayleigh number for the sun, it's of the order of 10 to the power 24. So that's a huge number, considering that the instability begins in a spherical shell at Rayleigh numbers of the order 10 power 6 or so, depending upon how thick the shell is. For the flat surface of the sort I was talking about, it's 1708 or some such number of the order 10 power 3. The geometry makes it different in this case. So it is many orders of magnitude beyond beyond the point of onset of instability. So you must expect the flow to be very complex. And the Prandtl number, which is the ratio of the momentum diffusivity to thermal diffusivity, both of which appear in the denominator of the Rayleigh number, is a very small number. And for water, it's about 5, and air it is of the order 1. And I will tell you why it is so small. So you have already some strange things that are likely here, and you compute the Reynolds number. It might be some huge number. And for people who work in laboratory, these numbers are immense. And you get a scale separation of the order of 10 power 9. That is the large scale, which is the depth of the flow, and the small scale, which may be Cole-McGrath scale, that we talked about yesterday briefly. And so this is really a paradise for turbulence aficionados, we might say, large scale separation, etc. But it's very much more complicated. The high level of turbulence activity, how can I estimate that it is even high level? I give you here some details of how I computed this, but I won't do that now. But when you have the slides and if you have the inclination to look at it more closely, you can do that. Now, I can estimate how effective turbulence is by doing the following. I look at the surface of the sun. Just a powerful telescope will do. And what you see is these granules. And the flow rises and sinks in these granules. And each of them, there's a big variation in size, but the typical one is of the order of 1,000 kilometers. And if you keep observing them for a while, these granules appear and disappear in the matter of about 10 minutes or so. That is their lifetime. So a 1,000-kilometer object sort of gets dissipated away in a matter of 10 minutes. That means there is a huge turbulent activity that is taking away energy from these scales, and that length scale and time scale will give you an estimate of the eddy viscosity of turbulence, and that is effectively in the range of 10 power 8 to 10 power 9 meters squared per second squared. It is meter square per second. I apologize for this. Yeah. Ridiculous. I should fix it. Now, this is only for the surface. Of course, I don't know what it is really inside. But we will make some estimates later on as to how large it is when we talk about mixing length and things like that. So the fluid dynamical question, which I'm embarrassed to say I've been thinking about for 30 years with no resolution yet, is that if the Reynolds and Rayleigh numbers are so high and the turbulence is correspondingly very strong, which I demonstrated to you in some way, how do these several coherent activities on the sun survive? And I will tell you what those coherent activities are. And the whole business of fluid mechanics of the sun really is this question, answering this question in my view. And of course, it has to do with not just convection, rotation, even though the sun as a whole is not a very fast rotating object. For example, if you calculate the Raspy number, where the rotation rate appears in the bottom of the definition, the rotation rate should be small if it is fast rotating object, but it is of the order 1. In fact, it's larger, much larger than 1. So even though it is so, it plays a very important role. And of course, There's stratification because the temperature varies so enormously from bottom to the top, and there are magnetic fields, and somehow they all pull themselves together to give you whatever you see. How does this really work? Okay, so that's a very major question in my view, and something worth spending some time on. So what are these coherent activities? Just to illustrate the most important one, you have, as a function of time, 400 years of sunspot observations, probably began around here. Galileo was not the first one to have observed it, although everybody thinks Galileo was the one because his PR machinery was very high. So everybody thinks Galileo did it first. There were many others, except for this period, which we don't understand. You see these number of sunspots on the surface of the sun, which are just magnetic activities that sort of go up and down, and the period is 11 years. You see, this period here is 11 years, approximately 11, and it varies a little bit from one to the other. So it is not exactly like clockwork. So there is some chaotic behavior to that, but it cannot hide the fact that there is an underlying periodicity to the phenomenon. Now, you might ask what really happened there. For almost 100 years, there was very little activity. It may be because they were not observing as well as now we do, you might say. But actually, there were people who were very committed to sunspots around this period. And imagine a young person who is committed his entire life to measuring sunspots, and he finds one sunspot in 1 year or something like that. So that was in fact the case. So you have to be lucky somehow, sometimes. What's that? They were monks. They were medical scientists and people like that who did it all out of their personal interest. Of course, if you resolve it even better, you can see that that is how it is. So it's a kind of very turbulent activity. So there is this background turbulent activity we discussed, but there underlies this essentially periodic phenomenon. And it is related to the magnetic activity on the sun. So here is the sun, and these are the field lines. So at one point, let's say that's a north and that's a south, and the magnetic field lines go like that. And on the rest of the surface of the sun, there is not that much. That means if you look at the surface of the sun, it looks really very quiet. And if you look at the count the number of sunspots, it is very small. I mean, on this one, there is nothing. So let's say 8, maybe some small number somewhere. But a little bit later, what happens is that that is 11 years later, the North Pole becomes the South Pole, and the South Pole becomes the North Pole in magnetic sense. And during the reversal of this, from the north to the south, the magnetic activity is all over the place. And there are these sunspots. This is the one that you actually count and plot. And so it's maximum around this kind of period when the magnetic activity is all over the sun, and minimum when it is well organized like this. And this goes on and on like this, so far as we know, for a very long time. And for your amusement, I obtained this a picture again from a NASA website. So this is the sun hidden under this green and the magenta lines. Green is one polarity of the magnetic field, and this one is another polarity. And so this is, I show you a video of 16 years of sun's magnetic activity compressed into 25 seconds. And you can see the time here. I just say it's negative and positive, but it doesn't make any difference. So that's how it happens. So you see now already what was at the top, originally green, is now becoming magenta. It does oscillate a little bit, but it will eventually settle down to magenta. So that's an amazing thing. It's amazing that it happens. And it is related to this differential, so-called differential rotation in the sun. So the sun is rotating, of course, from west to east. It does not rotate like a solid object like Earth does. What it does is the middle part rotates faster than the poles do. And it takes about 27 days or so for the equator to go around once, whereas it takes 34 or 5 days for it to go around at the poles. And if you measured angular velocity as a function of this latitude, you will find something like this. The zero is somewhere there, so it's going from 340 to 440 in some units. So now this differential rotation is actually, we know a lot more about this, and if you want to, you have to really explain all this. So this is now the radius of the sun, and until about 7/10 the radius, all latitudes rotate at the same speed, like solid body. Now after that, different latitudes rotate at different speeds. Zero, that is the equator, at 470 or whatever units, and at 75, which is close to the poles, 350 or thereabouts. And there is a lot more known about it, especially if you want to apply something like Taylor-Proudman theorem, for instance, to discuss the structure. This tells you that that does not work. It simply does not work. Okay, so I'll skip that a little bit and come back to it later if necessary. So skip that one too. Now you want to understand, let's say, things like this, and there are many more things you would like to understand. What do we have at our disposal? We have theory, of course. And since it's a highly turbulent flow, we think we know a little bit of turbulence, so we can use that. And there are many instability modes that are possible, especially in a rotating system. So we have that theory. And you can do numerical simulations nowadays. You can do different types of numerical simulation. Yesterday, you went through a particular device for calculations, but the numerical simulations are many different types. Some of them care a lot for the geometry, that is, take spherical shells and sort of ignore many other things, because the sun cannot be calculated in its greatest glory, because the Rayleigh numbers are so high, the scale separation is very large. You cannot do that. So different numerical simulations make different types of compromises. For example, as I say, some take care of the geometry and some boundary conditions, and some don't care about the geometry, but simply ask, well, what happens at very high Rayleigh numbers and very low Prandtl numbers? So you can learn a lot from all of them. But of course, as I said in the beginning, calculating an astrophysical object in its full glory is just not possible. And then the most interesting thing is that there are observations that have been going on for many years, satellites, as well as ground-based instrumentation. And this answers the question that Eddington asked in this book. What appliance can pierce through the outer layers of a star and test conditions within? You can't send a probe, unlike, let's say, other planets. And the answer is this so-called helioseismology. I will say a little bit about this in detail later. Basically, it employs two methods, let's say. or two classes of methods. Sun generates a lot of sound waves because you have a surface of the sun where the density gradients are extreme. No. You will see that it is very less dense, but the density gradients are very large. And there are these convective stuff that is coming from the bottom somehow. They somehow hit the surface, and it could even be supersonic on the surface occasionally. Although in the rest of the convection region, it is not supersonic at all. It generates sound waves, and these sound waves go around in the sun. They travel through the sun's interior, refract and come back to the surface and so on. And during the course of their propagation, they go through the sun and therefore have suffered the consequences of flow. So, which we will discuss very briefly later. And therefore, by looking at the sound waves, you might infer something about the velocity field in the interior. That's the traditional helioseismology. But now the data have been available for so long that you can actually compute the velocity field on the surface itself by following tracers on the surface or features on the surface of the sun. And as I said, there are many years of data now. And now you can do many more things. I have to say machine learning one more time there, for instance. So let's see what the theory tells. First of all, the theory of turbulence. But all of these helioseismology methods suffer from the fact that you only know what is happening on the surface and you infer what is happening internally. And this is by inverse methods. Inverse methods are notorious for their problems. But over time, people have been very conscientious in developing good methods. So you can take them with a reasonable understanding. Now, in convection, normal convection, what happens? I have fluid at the bottom, which is heated, and the fluid at the top that is cooled. So the heated fluid now becomes less dense, and it rises against gravity. And as it cools, as it rises, it becomes more dense and it falls down, and you have this repeated pattern. And this fluid motion carries with it the thermal content from the bottom to the top, and the whole thing goes on. Now, therefore, you need a temperature gradient that is a negative with respect to the vertical direction, that is the direction opposite gravity. Or if r is the radius of the sun, you might have said that, well, dt dr is less than 0, and therefore convection should occur. As I was trying to answer the question there, at the bottom of the convection region, the temperature is 1.5 million Kelvin. At the top, a few thousands. So this condition is definitely satisfied. But that's not enough, because you remember that there is hydrostatics that operates independent of any motion. The temperature at the bottom is high, but also the density is high. The density is high because gravity of the sun is just attracting the fluid. So in fact, if you just heat it a little bit, it's not enough. It does not make the fluid elements at the bottom actually rise to the top. What you need to do is to have enough gradient that will be in excess of the hydrostatic value. So what you're interested in is the difference between this and the adiabatic value. As I said, hydrostatic sets up huge temperature gradients. So convection is possible only if the actual gradients exceeds the hydrostatic values. And this is the insight that Schwarzschild had. So as a function of radius, the temperature in the sun is, of course, like that. This is the, let's say, the bottom of the convection region, the top. But unless the actual temperature gradient exceeds that of the adiabatic thing, that is, it is like that, convection does not happen. So that's the first important thing to know. And so the question to ask is, how large is this difference? So in order for us to understand anything at all of convection, that's something we should answer. Now, this is the answer to the quantitative answer to the question I asked already. Plotted as a function of the radius. This is the beginning of the bottom of the convection region. This is the top of the convection region. The temperature is plotted here on logarithm to base 10. And it's so, as I said, 1.5 million Kelvin here. And then it comes down. It's in the last 1% or so, it drops really very precipitously. Likewise, the density, it's a few hundred kilogram per meter squared here. And it's slowly varying, but towards the end, it drops off very fast. Because of the radiation, it just takes away a lot of energy very rapidly. And likewise, the pressure. So you see, you have a huge density and temperature and pressure gradients. And somehow you have to take that into account, which means the stratification of these things is absolutely important. And in the outermost 1% or so here, things are happening in a very different scale compared to what's happening in the rest of it. So it is sometimes convenient to think of convection in this part as somewhat different from the convection in the rest of it. In fact, surface convection, outermost 1%, deep convection, everything else. What you see on the using telescopes and things like that is this outer convection, how it is obviously connected to what happens here, but how it is connected and how the length scales and time scales change from here to here is something we should answer. So the theory, as I said, let's start with mixing length theory, which is due to Prandtl, same Prandtl that Grisha was talking about earlier. What it says is that in turbulence, we know that there are many scales, many length scales, and many time scales and things like that. But yeah. Yeah, you probably know this already. Jörg Schumacher and I calculated these numbers very recently, a few years ago. And it takes a little bit of work, but there are formulae which tells you what happens in ionized gases, how you can calculate various transport coefficients and all these things. So it's basically sitting down and calculating it with some patience. So the mixing length theory assumes that while it is true that there are many scales, length and time and velocity scales, there's only one length scale that matters. And that length scale is known as the mixing length. So it was already discussed earlier. Somehow I have this sense. Somebody asked me a question yesterday. So what does it mean? Think of turbulence as consisting of parcels of fluid of a certain length scale. And these parcels, they propagate in the fluid, and they go a certain distance, which is actually related to their dimension. And then during their transmission, they don't do anything. They don't exchange any momentum. They don't exchange any thermal energy, etc., with the ambience. And then when it reaches its predetermined distance, it just gives away all its properties. It's like a miser who doesn't give any money to anybody during one's lifetime, but when he dies, or she dies, let's say, it's now given away to whatever the state, mostly. Now, here it is. So this is a parcel of fluid, and this parcel is rising. I said adiabatic rise because nothing is being exchanged. And then it reaches this height, which is the mixing length, let's say lambda. And then it gives away whatever, it was hotter here. So it gives away that heat to the ambience. And of course, it expands as a result. Likewise, you have a cooler substance at the top, and then it falls and shrinks here, and then exchanges its coldness with the ambience. So that's the spirit of the mixing length theory. I took this picture from somewhere in the internet, so it's not mine. Now, this can be applied to the sun. And Erika Bohm-Wittense, who passed away some years ago, I put her picture up because it's very rare to see in astrophysics many women. And I hope it will change. But there are many other papers where you can discuss. I will discuss that. And I will tell you an extraordinary result that appears as a result of this simple calculation. I hope you will feel how extraordinary it is once you see it. So there is this parcel of fluid. It's the heat flux connected to that is the temperature difference, effective temperature difference. Here is the velocity and the specific heat density, etc. And this delta T is the effective temperature difference between, let's say, the beginning of the journey of the parcel to the end of the parcel, end of the journey. As I said before, it's actually not the real temperature difference that matters. It's the temperature difference minus the adiabatic value, right? So in fact, what I should then do is this delta T, I must take not this dt dr times lambda, which would have been the case if there were no adiabatic change, but really this temperature difference times lambda. Now, we don't know what lambda is, and we will do something with it pretty soon. And the velocity you take as the free fall velocity. Free fall velocity means that when you have a temperature gradient, the parcel fluid keeps accelerating initially, and then after a while it settles down to a certain velocity, and it turns out to be proportional to this delta T squared. And but you know how much heat is being radiated from the sun. This is just knowing the surface area of the sun and the temperature and using just Boltzmann's law, for instance. So you make these calculations. This is the total amount of luminosity of the sun, etc. This is not very complicated. You just have to keep track of things. Then you have this result, and you put in all the numbers on the right-hand side. By taking this mixing length with the scale height, that is the density varies, right? So the density varies, and you say, well, it varies sort of exponentially. Therefore, in a certain distance, the density falls by a factor E, that is the scale distance. And let's say I put it as equal to, but you can take it as proportional to, with a proportionality constant, which is of the order unity. But if you do that, you get the result that it's 10 power minus 7 Kelvin per meter. So what this is saying is, in this extraordinarily hot object, you have to go 10 power 7 meters in order to see 1 degree Kelvin effective temperature difference. That's a mind-boggling result that I was talking about. I mean, how do you even think about it like that? Does it really mean anything in the end? Is this true at all? This is what set me going initially.
Comparing to sun radius.
Yeah.
Is how many? Is 10 to 5, 10 to 6?
The sun's radius is 700 megameters. So the depth of the convection region is about 200 megameters. 200 mega is 10 power 9, right? Yeah. So it's not a lot of temperature difference that takes place in the convection region, the effective temperature difference. There may be 1.5 million here and 6,000 on the surface, but the temperature difference that participates in the convection activity is really very little. Now, this, of course, sets one going completely. Let me tell you that I have struggled with this for a long time. And in fact, if it is like this, well, I should be able to use constant temperature, constant density type of turbulence with which I am reasonably familiar. And I tried to calculate things, and it just doesn't make any sense whatsoever. So there's something mysterious going on. So this dTdr, that's an actual temperature gradient, exceeds this adiabatic value in this very small way. And this small difference, somehow it says two things to me. One is if the temperature difference is very small, it means everything is really mixed up very, very, very well, right? That's one way in which you can have very little temperature gradient. Another thing is that you absolutely need to have this small temperature gradient in order for any heat flux to take place at all. So the smallness says that it is well mixed, but its smallness also says that you need to have that small thing. It may be 10 power 7, which may be small, but if it were exactly 0, then of course it would not be possible to transmit anything at all. Well, I found that as an extraordinary result, you got it for almost nothing. I don't know whether it's true or not. We'll see. This adiabatic value, you can actually calculate this G over Cp. This really requires nothing but gas law and hydrostatics. You can do it in 2 minutes or less. And it is about 10 power minus 2 Kelvin per meter. So this ratio is about 10 power minus 5. So it's essentially adiabatic, but maybe a little different. And that suggests to you certain models of turbulence. But as I say, I try to apply them and I can't make any sense out of them. But here are the results of this. As a function of the radius, you calculate the various quantities like the length scale, lambda, and the mixing length velocity. Actually, it was done, you get this shape, or you don't get the actual numbers unless you assume lambda is proportional to the scale height in some way. But you assume that knowing what the surface velocity is, and you sort of match it, and then the rest of it follows like that. And if you calculate again a Reynolds number on the mixing length velocity times this mixing length, you get a Reynolds number like 10 power 12, something like that. And the eddy viscosity is 10 power 9 meters per second. Here I have the units right for change. And that's not very different from what I had calculated for the surface earlier. In fact, here I use simulations of this temperature gradient minus the adiabatic value. You see, it is almost 0, almost all the way until it hits the outer percent or less or something like that. And then it becomes large. So you have essentially adiabatic conditions and super adiabatic conditions near the surface, and which is one reason why I said it may be more convenient to think about convection here and convection here in different ways. And so, as I said, my calculations didn't make any sense. Then I was struggling with it, and Shravan Hanasoge appeared in my life. So I asked him, can you actually compute this from helioseismic results? He said, yeah, I can do that. And through him, I also got connected to Laurent Guizan, who is the director of the Max Planck Institute in Göttingen. And Shravan is now a professor in Tata Institute for Fundamental Research in Mumbai. So I learned a lot from these two gentlemen. And I want to tell you what they did and why it set me back several years. So what did Shravan do in particular? So here is the disk of the sun. And if I set this video going, you will see it oscillate a little bit. You can see that better in the middle of the disk rather than on the periphery. Although on the periphery too, if you watch this very carefully, you will see it oscillating. And what you find is the sound waves on the surface of the sun. So this is whatever you observe on the sun is filtered out in the right range to give you the sound speed, sound waves. And if you pay attention, you can see that it oscillates here a lot. And of course, here too, if you can look as I can from this distance. So now from these sound waves, you try to estimate what the velocity is on the, not just on the surface, but on the inside of the sun. And how is that done? So, yeah. Yes, yeah, yeah. So I have here the disk of the sun. And A and B are 2 points on the surface. Now let's say at A, there is a certain sound wave that propagates into the sun. So I'm using ray hydrodynamics or something. That is to say, I'm not worried about the wave fronts and wave structure and all that. Now, for a certain wavelength, it propagates like this and it refracts because it is moving into a denser medium as it gets closer. So it sort of does that and it establishes a reverberating normal mode. So if the wavelength were smaller, it would do the same, but with a greater number of cycles. If it were even smaller, you of course have this on the surface like that. So the thought is that the sound waves are not generated by me or you or anyone, but they're generated by the dynamics of the sun. And now, let's say I want to, if there were no motion in the sun at all, everything was quiet, the time it takes for the sound wave to go from here to here would be identical to the time it would take for it to go from here to here. So there is perfect symmetry. On the other hand, if there is a velocity in the flow, I mean in the sun, along the path of this ray, if the fluid is moving in the direction of A to B, it takes smaller amount of time for the sound wave to propagate from A to B than it would take from B to A. So the flow inside breaks the symmetry, and somehow that knowledge of the time difference is what is needed in order to tell you what the velocity is. So a little bit more. Let's say this is the wave pattern between A and B, and I'm looking at some pattern like the maximum in the sound wave. And this is, let's say, T minus and T plus, which is the taking some arbitrary position. And if there is no motion in the inside, T plus and T minus would be the same. And then, of course, they are not. And you will have a time difference. And the time difference you have to somehow convert to velocity. And to do that, you have to have a model of the sun. And so it is not a direct answer, but you can do that. But the point is that so far what I've said is, it's telling you something about the flow along the path of the ray, but you actually want local measurements. And how is that done? It is done like this. So let's say looking down into the sun, this is the pole or something like that. And this is the surface of the sun. And I'm interested in, let's say, the velocity at this point inside the sun. And different sound waves going through the point will be like this. This ray will go like that, and that ray will go like that, et cetera, et cetera. Now, this will be sensitive to everything. But if you average the result of all of this going through that point, then you get the data for the velocity just at that point. This is the local helioseismology. And this, as you can see, it is complicated. And in fact, there were some errors in what we did earlier. And in the meantime, also these wonderful simulations called ASH simulations. That's actually Yuri Tumre's group here, Mark Mish, from whom I learned a lot through many discussions. And this ASH means Inelastic Spherical Harmonic simulations. They are really calculating the flow. This Inelastic Approximation is superior to Boussinesq approximation in these cases, but it doesn't do the compressible things fully, and so filters out all the sound. So they had this domain which is almost the same as what you want, except that it doesn't go all the way to unity, because as you remember, in this last bit, everything changes very rapidly, and there are boundary conditions. The only thing about it is it could not calculate the whole business, so it assumed the viscosity to be some very large value, some 15 orders of magnitude larger than it really is, and the thermal diffusivity like that, also some large orders of magnitude different. The Prandtl number, which, as I said earlier, and I will show you in a minute, is very small, but they assumed it to be of odd unity. There are many versions of ASH simulations where they take different values, but essentially like that. So we were able to make a comparison of everything that was known at the time in this paper. So this is the angular degree. You decompose the motion into spherical harmonics, L, M, and N. So L is the one that I'm plotting here on this axis. It's like wave number if you want. And this is the energy contained in those wave numbers. And these were the results that Shravan got. Actually, he got it slightly different ones, but several years down the road, Aaron Bish in Laurent's group actually recomputed the whole thing and found little errors, like a 2 pi was missing here and a 2 was missing somewhere else. It's a very complicated calculation, as you may imagine. And he fixed all that, and that is the result. And Mark Mish had this theory, which gave that. With his permission, I changed his theory from a horizontal line to this line. So he assumed that it was constant energy at all wave numbers. I said, Mark, how does it have to be constant? You know that in turbulence at low wave numbers, it goes according to some power. And am I allowed to keep the same energy, but allowed to plot it the way I want it? He said, okay, go ahead. So I have his permission. So that's what you find. But the ASH simulations gave this answer. And there was another thing also coming from Boulder, which gave you this answer. So this is now a very worrisome result, which is right. Yeah. The jagged thing. No. This flat I changed to this one. Yeah, red. But the actual measurement is this. The helioseismology result is that. Now, some people like this result a lot because it explained to them some of their own prejudices. Some others were not so sure. They were also very polite to say, maybe you are comparing apples and oranges. And perhaps that is true. So then I prevailed on my Japanese colleague, Hata, to do simulations and Shravan to do this helioseismology of identical quantities. No longer do I have the excuse that, well, maybe they were doing something else and you are doing something else, you find the same result. At 87% of the radius, this is what the simulations show, and that's what the helioseismology measurements show. Basically, the energy at low wave numbers is overestimated by the simulations. So you have to understand that. Of course, eventually it will have to come down, but you don't have any confidence in helioseismology results if you go to higher wave numbers and things like that. So I think that is a good result. It looks like that is reliable. And so, sorry, yeah.
So was it results from different methods of calculating?
In the previous one, yes.
Okay.
They were supposed to be the same thing, but they were not tailored by construction. You know, people say, yeah, this is the spectrum of velocity fluctuations at a certain height, a certain distance. But they were doing whatever they thought was the right thing, and we were doing whatever we thought we were doing the right thing. But whether they were exactly the same was just hard to ascertain, because they're all very complicated calculations.
And probably different parameters, right?
They are different parameters for sure. Yeah, different parameters for sure. And that is something we will discuss just now. And my thing has always been that the Prandtl number is very low in the sun, whereas all simulations use, FRD unity, or most simulations do. And the conditions are extremely non-Boost-esque because the density and temperature, they're changing so rapidly across the height. And of course, there's rotation. And then Jörg Schumacher, who was my postdoc many years ago, came to visit me as a professor, visiting professor for 1 year. And he was asking me, how should he invest his time? Should he invest his time on doing large aspect ratio simulations or go to low Prandtl number? My credit is that I convinced him to go to low Prandtl number. And and then Ambrish Pandey, who became Jörg's postdoc and became my postdoc later, now he is going away as a professor. They did the simulations. I am a part of it. And I'm shamelessly listing for you some papers we wrote recently. But now let me tell you what we find. This is the answer that you already know, but which I gave. This is a paper from that we wrote with Jörg. This is the radius of the sun. And here is the logarithm of the Prandtl number. And this is the curve. Logarithm to base 10, so the Prandtl number is about 10 power minus 6, remains essentially constant, except here, where it changes very drastically. And of course, the numbers cannot be depended on here because the gas is only partially ionized and one doesn't know how to do these calculations right for partially ionized flows. Nevertheless, that's what the result is. And why is the Prandtl number so small? Why is it of the order unity for air? Air, for instance, you have molecules moving about, and they carry with them the momentum as well as the thermal energy. So they are both really comparable. And in fact, they are coming from one and the same thing. But here, it turns out that the momentum is transported mostly by electrons. And you can actually calculate the viscosity and the mean free path, all this kind of stuff. Whereas the heat transport is taking place by photons. The photons that come from the bottom of the sun, they emerge outwards. They carry the heat flux. So in fact, these are done by very different animals, except of course there's some overlap, which is what makes it possible to say there is a Prandtl number in the flow. And you do all the calculations, you get this number. This number was not calculated before like this by anybody as I know, but people knew already. It's therefore not a earth-shaking result, which is new. But the thing is, it is what it is. It's so small. So now, what is the effect of this? People told me generally that yeah, it doesn't matter because you have a fully turbulent flow, and if you have a fully turbulent flow, what does it matter what the molecular properties are? But actually, that's not true. That really is simply not true, which is part of the story. So here, for one Rayleigh number, which I cannot remember, Jorg calculated the mean temperature gradient for a different Prandtl number in a laboratory convection. So this is the bottom. This is the top. The temperature is plotted on this axis. So it is cold here, which means it is top. This is top and this is bottom. So normally what happens is that there's a boundary layer set up on this wall, the top wall, and a boundary layer set up on the bottom wall. And a lot of the temperature change takes place in the boundary layer. And then during the main part of the apparatus, so-called bulk, let us say, it's essentially constant. Like we had in the sun, we just more or less said it is very close to the adiabatic value. Now that would be true for Prandtl numbers of odd unity. If you go to higher and higher Rayleigh numbers, this becomes sharper and sharper at the boundary layers. And then in the most of the flow, it is essentially constant.
But you also have a green, which is opposite.
Yeah, this is a high Prandtl number, in which case, the plumes sort of have a tendency to really not mix until you get to a certain height, and that's why they are hotter and things like that. But I will not want to dwell on that. But what I want to dwell on is that you go to lower and lower Prandtl numbers. For example, this one here, the profile which was like this becomes like this. This you would learn in your high school, for instance, is approximately the conduction profile. When you have only conduction as the transport mechanism, there is the bottom flow and there is the top, and the temperature is going linearly from bottom to top. So it's not very surprising that the Prandtl number goes very small. That is, the thermal diffusivity is much larger than the viscosity. Therefore, perhaps it is not very surprising. But I want to make a wild conjecture, which is based on a few simulations. And let's see what it means. So if I increase the Rayleigh number, this linear thing changes again to something like that, let us say. But I go down a little bit more in Prandtl number, I get back the linear. So essentially, let's make a conjecture. For any Rayleigh number, however high, this looks like a ridiculously positive statement, but it's a speculation. For any Rayleigh number, however high, there exists a low enough Prandtl number below which heat transport is accomplished mostly microscopically, that is by molecules or by photons, something like that. Well, I didn't know that it was true. So Jorg and Amrish calculated many flows with varying Prandtl number. So here is 2D simulations. A Prandtl number on this axis going from 10 power 2 to 10 power minus 4. 10 power minus 4 is still not 10 power minus 6, but it is small enough. And you can see the effective Prandtl number, which is the effective viscosity to effective thermal diffusivity. This is what the turbulent Prandtl number, this is the one that everybody is very fond of using. It increases according to some power law, which is about a third here. But if you go to 3D, is the same power law, but the power law is -1. That is, it's if you go in Prandtl number, go down in Prandtl number, the effective Prandtl number just goes up by several orders of magnitude. You extrapolate it, assuming it is true, to 10 power -6, which is here. So the effective Prandtl number will be somewhere there, which is a few thousands or tens of thousands, something like that. Now, what does this mean, or why is this important? So, so here is the same result with some other simulation. Let me put all this together. By the way, the main idea that I'm going to describe, although never done in this fashion before, is due to Mark Misch, who is from Colorado. I don't know exactly what he's doing now, and others. So what is the effective Prandtl number? Effective Prandtl number means, I had the definition somewhere, maybe I erased it. Okay, it's here. Viscosity to thermal diffusivity. Now, suppose you start at some point, t equal to 0, a velocity fluctuation and a temperature fluctuation. For simplicity, take them as sinusoids, yeah. ADS, yes. T is turbulent in my head, and that is the effective thing. So let's start with a velocity and temperature, which are which have some amplitudes like this, take as sine waves. So a little later, what is the fate of these disturbances? Because this one here is very large, that means the effective viscosity is so much larger than the effective diffusivity. Since the effective viscosity is very large, it will kill off all the velocity perturbations, okay? It will just kill them off. Whereas in relation, the diffusivity, the effective diffusivity for the heat is so much smaller, therefore it will not do anything for the temperature fluctuations. So schematically then, at a later time, I have a velocity fluctuation that has diminished, but the temperature has sort of remained the same. What it means is that if I started at the bottom of a convection region with a certain pattern of temperature fluctuations, they just go from the bottom to the top. I'm sort of exaggerating a little bit. Just go from the bottom to the top as if nothing happened in the flow, as if the turbulence that existed didn't matter to it. It just managed to go through. Whereas the velocity fluctuations become are subject to the usual laws which diminish them as they propagate upwards. So you have a very peculiar situation where the background velocity is sort of behaving like a normal turbulence, whereas the temperature fluctuations are not behaving like that. This to me was an answer to a long-standing puzzle I had. And so if I calculated some numbers, they begin to make a better sense, but I will not take you through all of that. So here is in the simulations done by one of them, you see these temperature perturbations going from bottom of the convection region to the top without being influenced by the turbulence that sits there. And another thing that happens is that if you allow for non-Boussinesq conditions and so on, this is again the height of bottom plate and the top plate. These are simulations in a laboratory. Normally, if it was perfectly Boussinesq case, what would happen is in this boundary layer, half the temperature would drop, and in this boundary layer, half the temperature would drop. In the middle would be the mean value, which is half. It's 1 at the top and 0 at the bottom. Excuse me, just the other way. Now, however, because of these non-Boussinesq effects, what happens is that the temperature drop in the boundary layer with high diffusivity is like that, and the mean temperature sort of stays, doesn't come down to half at all, but it stays at like 90% or something like that over the bulk. In other words, the temperature inside the convection region is not set to be the mean value between the bottom and top. Mean meaning after you subtract the adiabatic value, it's not even that at all. It's actually mostly what happens at the bottom, and for most of the case, and only towards this end, it drops precipitously, like some of the pictures I showed you earlier. Another thing that happens is that the length scale is set by the one with the higher diffusivity. And as you go up, this is from the bottom and you go up, the major length scale remains the same, whereas smaller and smaller perturbations get added on top. So that's the result of these simulations. In my view, very important, although I admit readily that it does not include spherical shell geometry and things like that. But what it tries to do is to push the parameters into the domain that are of interest to the sun. I summarize for you some results. The layer with higher thermal diffusivity controls the structure of convection. So if I have top and bottom in the sun's case, for instance, some people have speculated that the convection is set by what happens in the top surface because it radiates away, and it gives rise to plumes, and those are the ones that actually drive the flow. But if this is true, it actually is the one at the bottom that sort of determines the structure of the convection, and the heat transport does go down because the temperature and velocity field become increasingly uncorrelated. I have diagrams, but I will not show you. Temperature field becomes smoother and velocity field becomes more and more intermittent. Energy moves from smaller to smaller scales, which is one of the results that I was very concerned about earlier. And that what you see in the spectra. And if it is true for the sun, the convection region does not begin probably much later than people assumed. If you read the literature, people even tell you that the convection begins at 0.713 of the radius, going to 3 decimal places. But if this is true, if a Prandtl number has such a huge effect, it's not very hard to argue that this must be the case. Okay, now I will take you in the next 10 minutes or so, which is, I hope that's how much time I have. Yeah, okay. I will take you through what I consider a revolution to be happening in the sun's dynamics. And that is, you can measure the velocity on the surface without having to worry about sound waves and things like that directly. And that's because you have data collected over many decades now, and you keep averaging and averaging and averaging until you get some sensible answer. That's really all it is. I mean, I make it sound very simple. One of the ingredients of the model of the magnetic activity is that on the surface of the sun, this is the convection region, there is on the surface a poloidal motion going from the equator to the poles, and to compensate for that, you have a motion coming down like this near the bottom of the convection region. This is the meridional flow, and its magnitude is about 10 meters per second. People have tried to measure this before, and in fact, taking the data for a very long time, it wasn't very much data there. You get something like that. But actually recently, Laurent Guizan and his colleagues have measured it and have actually given you a profile that is exactly as expected. So I'm taking a cut along here. Top part will be from left to right and bottom part here, just the way I have it here. So that's one result. And the more interesting result to me is the solar inertial modes. Inertial mode simply means that these are normal modes of the period corresponding to rotation rate, something like that. And essentially, you need a rotation in order to see them. Now, this picture you recognize in any weather map. This is looking down from the top into the Earth, not into the Earth, on the Earth. And these are these azimuthal waves, and these are the Raspy waves. And Raspy waves, if you have a shallow spherical shell, you will have these modes that are set up because there is a change in the Coriolis force as you go from lower latitude to higher latitude. As you know, the Coriolis force goes like sine of the latitude. So on the equator, it is 0, and as you go towards the poles, it becomes very large. These Raspy waves are the ones that actually drive a lot of the weather. For example, jet streams and things like that. Now, why don't we expect them in the sun? Because after all, it's a spherical shell, just like it was deduced in the model of Raspy. And there is change in the Coriolis force as you go across latitude. In particular, because of differential rotation, it could even be more significant. But it was not attempted for a very long time because the data were not there. You could calculate anything you like, but what's the point of it? But now there is so much data. And in fact, the initial speculative paper, which is somewhat speculative, by Scott McIntosh and Dick Patti, others here in this paper. And the one that actually made the first measurement is Lopin. This is Laurent Guizan's group. And then Hannes Soge came along, and there are these other papers. And this is a kind of a nice summary. So are there Raspy waves on the sun or not? I explained to you a little bit here the result of conservation of vorticity, that is radial vorticity. And if you have a parcel of fluid that has a certain rotation and it changes position from one latitude to another, because of the Coriolis force that has changed, it has to adjust its vorticity when it moves up or down. And if you set it up, it turns out it will produce a wave. And these, as I said, were helioseismically measured in this paper, which is this here, Nature. And they found these waves. I'll come back to this slide again. Forget about this top part, but here. And how did they know? If you calculate the dispersion relation, this is the frequency versus spherical harmonic of the velocity you measure. This is what is supposed to follow if you really had Raspy waves. And that's what they found, you see. On this horizontal axis is M here. I don't know why it's M. There's a frequency, and these pixels are what they found from the data, and that's the theory. So of course, you would expect something different happen at very high azimuthal order, but basically you get the result that you expect, which I think is amazing to me, actually. And what Laurent did was use this at the bottom of it somewhere, maybe. I don't know where I put it. What Laurent did was to actually get bounds on superadiabaticity, that is the thing we calculated to be 10 power minus 7. He estimated this to be like that, and this viscosity to be 100 kilometers per second, which is not very different from what I had estimated earlier from other means. So basically, I think things are sort of falling in place at little places. But the truth is to integrate all these things into the big picture. This is what I'm driving myself towards. And I wish we could spend more time on this, but I am not so confident myself. So as a more or less a summary, various forms of inertial modes are being explored currently, not just the Raspy waves, but there are many other modes that are possible, which you can pick out from measurement or helioseismology. I call that measurement. It really is observation plus a certain method of calculation. And then many new ones have been found. For example, Chris found in this paper, with which I had something to do, new modes. Now there are people thinking about applications of the Raspy waves in predicting space weather. Assume that near the bottom of the convection region, these Raspy waves develop and they reach the surface of the sun, for instance. It's possible that some perturbation at the bottom of the sun will actually travel all the way to the surface and may in fact escape like one of the solar flares, for instance. If that is true, then it is a way of calculating the space weather. This is what I said, we want to get to that point. But anyway, attempts are being made. Dikpati, she's here in Colorado, for instance, in UCAR. And her paper in this et al. Somewhere, my name is also there. A possible generation mechanism for Raspy waves in the sun, where they happen, how they propagate, etc. All so far very speculative. So I should conclude now. So my conclusions are the following. The sun has been the subject of systematic scientific observations for several hundred years. There is no other object, celestial object, that we can make that statement for. And some fluid flow aspects were known already in the 1830s. Of course, when Galileo saw the spots moving, he already knew there was flow on the sun. It was not just some fixed object. But, then there were people in the 1830s already thinking about the flow. And in 1930s, big change happened because a turbulence literature on mixing, etc., began to have an influence on astrophysics problems. Now, many people have computed things, not only direct numerical simulations, but also using large eddy simulations, so-called very large eddy simulations, added diffusivities, etc., through which I did not take you, but it is important to know serious work is being done. Now, there are many ideas, and now they are amenable to verification by careful observations by helioseismology. The problem, of course, with helioseismology is that it is an inverse method, and okay, you have to live with it. Progress in the last 20 years has been exciting because there is something to compare with instead of pure speculation, as it happens in many parts of astrophysics, for instance. Not a indictment on the subject, but that's the way it is. Now, not only sound waves, but direct measurement of surface velocities are possible. And compatible instability modes like the Raspy waves have been proposed, and also as a predictive tool. And the new missions, they're there, and the new technologies being developed. And I'm very optimistic that in 10 years from now, we will know a lot more. If I were to give a talk 10 years from now on this subject, I hope much of it will be very different. So thank you very much. Yeah.
Professor, I have a question about those thermal convection simulations.
Yes.
So most of them have not included MHD effect.
Yes.
True.
Yes.
So how important do you think?
Yeah. So MHD clearly is our magnetic fields are very important near the surface, especially for the sunspots and things like that. But the point of view that I have taken for our presentation today is simply that magnetic field sort of rides over the velocity field. And I do not want to bother myself with it unless I am really directly involved in magnetic activity. It may be true or may not be true, but certainly on the surface of the sun, where the magnetic activity is enormous, magnetic buoyancy is very important. It has an impact on the velocity field as well, which I did not include. But presumably internal to the surface, the magnetic field is not having such a huge impact. This is also speculation, but a plausible speculation. What is that? Eddy viscosity. Yeah, eddy viscosity is like this. If you have a normal flow, laminar flow, what viscosity does is it smooths out all perturbations. Okay. Now, if I have a turbulent medium, then I have a perturbation at a certain scale. Now, because there are fluctuations of all scales, some fluctuations take away energy from this thing that you put in. Okay. So that is not a molecular effect. It is just the fact that the nonlinear dynamics transports energy from one length scale to neighboring length scales. And that is the effective or turbulent viscosity. Okay, it has the character of viscosity, but it is not due to any molecular action. Molecular action basically is the same thing. It takes away energy and puts it into a molecular motion, right? It just increases the temperature and therefore the mean free path and all this kind of stuff. But now in a turbulent medium, you don't need viscosity until you get to very tiny scales. But at all other scales, fluctuations of smaller scale will take away energy from what you put in. That's the turbulent viscosity.
Like I'm looking at the turbulent medium and the larger scale, so I do
diffusion. You might say it is effective diffusion. Yeah, viscosity is a diffusive mechanism. Yeah, yeah, but it's not supposed to depend on viscosity itself, the molecular viscosity. It depends on the dynamics of the turbulence. It depends on how vigorous it is. It is very large in magnitude, then clearly it will take away the energy much more efficiently. And it depends on how big it is in terms of length scale itself compared to what you put in. If it is comparable, then it takes away energy more efficiently. If it is very small, it will not have the same effect. Yeah. The convection in the sun is primarily non-compressible. It's non-compressible because any estimate of the velocity inside the sun tells you it is very much small compared to the speed of sound. Only near the surface, occasionally do you get compressible effects. So to a first order, one should not be thinking about compressible turbulence. in order to understand what the solar dynamics is. But clearly on the surface, there are little shocks sometimes and things like that. But in the bulk, no. And so you can compute it. So ignore compressibility, let's say. You still have options. One option is the Booth-Nesk approximation, which you mentioned, I think, which simply assumes that the effect of the temperature difference between the bottom and the top appears only through the buoyancy term in the momentum equation. And elsewhere, you just take the density to be constant and everything will be okay. And this would be true as long as the temperature difference is small, then the top and the bottom are not very different. But that's quite often not the case, especially if you drive the flow hard. And then you have to make other approximations. One of them is this inelastic approximation that I mentioned, where you sort of allow for the variation in the density, but you still don't allow any sound waves. It's sort of intermediate between the two. And you will have to figure out under what conditions the right model is applicable. Right. Yeah.
Were there any major differences in the solar convection region?
Yeah, Booth-Nesk gives you, in my opinion, not very meaningful results for convection. Because after all, you have such huge stratification and the properties of the fluid, assuming the plasma to be just a regular fluid, at the bottom and the top are immensely different. Therefore, the boundary layer type characteristics are immensely different. And that's why I said what controls is the one with larger diffusivity. And that is not what you find in any Booth-Nesk case. So you shouldn't be thinking about Booth-Nesk at all, in my opinion. Yeah.
Question.
Yeah. It's wishful thinking is what I should have said. Yes. Yeah. Yeah. I only have a few low Rayleigh number cases, and nobody knows whether any. It will be very large anyway. Yes, which is sort of what I'm saying. Yeah, yeah, yeah. So I don't know if that is true or not, but at low Rayleigh numbers, at least it is true that if you decrease the Prandtl number below a certain level, if I tell you what the Rayleigh number is, I can tell you how low I have to go in Prandtl number to just forget about turbulence and only think about molecular type activity. Will that continue forever? I have no idea. And furthermore, for the sun, the Rayleigh number being so large, the Prandtl number has to be extremely small, and I don't even know whether it's true or not. But at least it's a way of thinking that helped me pretend that I understand something. Yeah. Gravity plays the role in all stars in the following sense. A star is a balance between gravity and pressure gradient, essentially. Because what gravity does is pull all the material, but the radial pressure gradient does not let it happen indefinitely. Otherwise, everything will be shrinking. So the size of a star is set by gravity and the corresponding pressure gradient that one develops. Yeah, that's the shape of the star. Of course, rotation adds a little bit of what do you call it, the oblateness, but for the sun it is very small. what is? No, gravity is G times M divided by R squared, where G is the universal gravitational constant, and mass is M contained within that radius, and the other M is the thing that is being attracted. So that capital G is the one that is universal, but the actual gravitational constant, which is whatever 10 meters squared per second for the Earth, depends on where you are along the radius.
There's a model of the tachocline
Yes.
that assumes that the convection drives a jet, and that's responsible for the differential rotation. So if the convection, though, now starts further out, is that model that?
Okay. He means convection. So I would dare not say anything is dead. But to me, it looks like many models that tell you that it's very highly turbulent near the tachocline don't seem to be right to me. It always bothered me that if the turbulent activity at the tachocline is so large, why is it that the magnetic field lines remain intact? As the sun rotates, these field lines wind around, as you know very well. Why do they even retain their integrity? So, okay, I believe that the actual convection starts at a higher radius, only based on the results from simulations and things like that, not of a spherical shell, not at such high Rayleigh numbers. So what in physics, this is the way it works, right? You sort of have controlled experiments under certain conditions, and you know that it works there, but you sort of extrapolate that knowledge to some other domain. But real physics will try to eventually bridge that gap and make sure that that is true. But I don't think we have gone there at all yet. So it's partly speculative at the moment. But eventually, if you have a full-fledged model that builds that in and still explains everything we know, then it would be correct. But so far, it hasn't gone to that level. But I would say that is my conclusion. Yeah.
I'll ask the last question. The Raspy waves are my favorite wave.
Yes.
I'm sort of amazed at this plot you showed.
Yeah.
Was it like nanohertz or something?
Yeah.
These are tens of years.
This is tens of
You're pulling
years.
out electricity correlate. It's amazing.
Tens
It's
of
amazing
years.
data now.
It is, yes. Tens
This
of
is 20 years of data.
20 odd years, yeah. So it has many, many rotations of the sun. And it's amazing. I mean, several people have independently done this, and they think that is correct. So to me, that's
You're
astounding.
getting vorticity, right? So
Yeah, so
you're seeing how do you get horizontal velocities out of?
So on the surface, you have the motion mapped out, let us say, and you calculate the curve.
So you're looking at features moving.
Features moving, yeah. And of course, you might readily ask whether those numbers are reliable and things like that. But the only point is that it's like I said earlier, average. And something will result, something will re-emerge. So you have to believe it. So that's the way it is. Yeah.
Let's thank our speaker.